So there are properties of vectors that you guys will need to know. The first of which is that you can add two vectors together. Pretty easy, we call it the sum of the two vectors or the resultant of the two vectors. So if we want to add vector u plus vector v, just add the x components of them and add the y components of them. Should be pretty straightforward. We can take any vector and multiply it by what we call a scalar, k, to make the magnitude longer, but we'll still have the same direction. So that's easy enough. You just multiply both the x and the y components by whatever that k value is. We talk about the opposite of a vector, means we just multiply it by -1. And officially, vector subtraction is defined if you want to subtract one vector from the other as the first one plus the opposite of the second one. Everybody good with that? Easy little things we can do to vectors. We'll just do a couple little manipulations with vectors just to make sure we know how those work, and then we will move on and start doing actual stuff with vectors. So if I want to do 2u plus 3v, what do you think the first thing that we will need to do is? Multiply, that's right. So first we'll find what 2u is. So what's 2u? 2u should be -2, 6. Well, that's what you guys got. Yeah, Ryan, I'll have these up. Oh, and not in Google Classroom. They're all the notes are in Google Drive, in the old Google Drive link. I sent it out there earlier this year, but yeah, the video, Ryan, will be on YouTube, and then the notes will be in Google Drive. I'm not posting them specifically in Google Classroom just because I gave you guys the link to the Google Drive. What about 3v? 3v should be what vector? (12, 21). Okay, and so 2u plus 3v, we just need to add them. -2 plus 12 should be what? 10, and then 27. Everybody good with that? Okay, if we're looking at u minus v, that should be the vector -1, 3 plus the opposite of vector 4, 7, which would be -4, -7. And so what would that give us? You got what did you get, Darius? You got -5 and hopefully -4, not +4. Yeah, -4. All right, everybody good with that? Easy enough. And what about the absolute value or the magnitude of 1/2 of u? First, we'll need to figure out what half of u is. So we'll say this is the absolute value or the magnitude of, and we can divide those by 2. So that'll be the vector -1/2, 3/2. And how do we find the absolute value or the magnitude of that vector? All we need to do is the square root of the x component squared plus the y component squared. So this should be the square root of -1/2 squared plus 3/2 squared. Yep, distance formula. That's right, Darius. And what does that give us? That gives us the square root of, let's see, that's 1/4, and that's 9/4. So the square root of 10/4, or the square root of 5. square root of 5 halves if we wanted to call it that. Or we could call it root 10 over 2, however you want to call it. Let's just do that. Root 10 over 2 sounds good. Square at the top and the bottom. Any questions or issues with that? All right, a couple more properties of vectors that you should at least be moderately familiar with. I think we mentioned before that v over the absolute value of v is the direction vector, or the unit vector has a magnitude of 1. Its component form is just cosine theta sine theta, so it's just telling you the direction. So that's how we get the inverse tangent of the y value over the x value from the velocity vector. It gives us our direction of motion. We have addition of vectors is commutative. You can do it in any order. It's associative. You can combine any two parts of it together and add them in any order. It doesn't matter. If you add nothing, if you add a 0 vector to a vector, you get the same vector. A vector and the opposite of that vector becomes 0. 0 times any vector is 0. 1 times any vector is just that vector. Basically, all these same properties that we have with regular numbers can be applied with vectors. So we have a times b times u. That's the same as a times b times u. You can distribute an a through the sum of two vectors, or if you have two scalar quantities that you are adding together and then multiplying by the vector, then you can just do au plus bu. So you can distribute the vector through addition, as well as distribute a scalar quantity through the sum of two vectors. Everybody good with all that? I think that stuff's pretty easy. It's all kind of intuitive, I think, since that's like all the same with our regular real number system. Any issues? Everybody good with that? All right. So let's do something with this now. We've got an airplane flying at 400 miles an hour. It's got a tailwind of 60 miles an hour. It's acting on at an angle of 30 degrees north of east, and we want to know what its new ground speed and direction are. So, any thoughts on what we want to do with this? What is this problem basically asking us to do? What do we want to know about the plane? We want to know how fast it's going, right? And we want to know what direction it's moving in. So those things are both found using what vector? How do we know how fast something's going? Which vector will tell us how fast it's going? Position vector, velocity vector, or acceleration vector? All right, velocity vector. Yeah, the velocity vector will tell us how fast something's going. And in order to find the direction of the motion of something, like an airplane, we have to take the inverse tangent of the velocity vector of the y over the x. So for both of these things, we need the velocity vector. So first, what's the position vector for this plane? Or actually, let's draw a picture first. Let's say here's our plane. It's trying to fly due east at 400 miles an hour. Okay, so this is what we've got going on here for our position, or for our velocity vector. And how could we write this as a position vector? What is the x component of the velocity, of the position of our plane? How fast is this plane going if we ignore the tailwind? It should be going 400 miles an hour, which, if we're talking about position, that would be 400 times what? If I've gone for 1 hour, how far have I gone in this plane? $400 miles. If I've gone for 2 hours, how far have I gone? 800 miles. If I've gone for 10 hours, how far have I gone? 4,000 miles. So what is the x component of this position here? It's 400 times what? Yeah, I'm gonna use t for time, but yeah, 400t is the x component. If it's flying due east, what's the y component of this position vector? Should be 0, right? Because it's not moving in the y direction at all. It's moving due east. So there's our position vector. So could we figure out what the velocity vector is? How do we find the velocity vector then? Just by taking the derivative of the position vector. So our velocity vector should be 400, 0. Everybody good with that? Hopefully. All right, so then what's happening to our plane? It's got a tailwind blowing against it at an angle of how many degrees? 30 degrees, right? So it's helping this thing speed up. And what is the magnitude of this? How hard is this wind blowing? Should be at 60 miles an hour, right? And so if we wanted to write a vector that represented the velocity of the wind, how would we do that? What is the x component of it? Should be the magnitude times what? Yep, times cosine, right? So it should be 60 times the cosine of our angle, right? Because that's telling us the x component of what that wind is doing, right? Cosine of 30 should give us the adjacent side to the angle, which is our x direction, and it's the magnitude times the cosine of that angle. And so what should the y component be? Should be 60 sine 30, yep. All right, so what's cosine of 30? It's root 3 over 2, so this is 60 root 3 over 2, or 30 root 3. And 60 sine 30 should be 60 times a half, or just 30. So the vector that represents our wind is 30 root 3 comma 30. And the vector that represents what the plane is doing regardless of the wind is 400, 0. So how do you think we should, what do you think we should do to figure out what the plane's new ground speed and direction is? What do you need to do with those two vectors? Add them together, exactly. So the plane with the wind should become 400 plus 30 root 3. That's the velocity vector of the plane plus the velocity vector of the wind, comma what? 0 plus 30 or just 30? And that's the y component of it. Everybody good with that? All right. So what is speed? How is speed represented in relation to velocity? Well, yeah, that's what we're getting to right now, Nick. Yeah. So what is this? We want speed, right? That's what it asks for. It says, what is the plane's speed? And so what is speed? It's the absolute value of velocity, exactly, Luke. And so this is our velocity vector. And so if we want the speed of the plane, then it should be the absolute value of this velocity vector. That will tell us how fast this plane is traveling. And so how do we find the absolute value of this vector? It's just the magnitude of that vector, right? And so we'll just do, I'm going to get a new page for this. We'll do 400 plus, what was it, 30 root 3 squared plus 30 squared, all square rooted. And that should be our speed. And so what does that speed come out to be? Max? What does that come out to be? Anybody do that? You're supposed to be doing that right now. And rounding it to 3 decimals. $452.956. Does that sound good to somebody else? Yeah. And that should be miles per hour. Everybody good with that? Does that help answer your question from above, Nick? Okay. Then the next thing it asks us, what's the direction of this plane? Well, our direction should always be found by doing the inverse tangent of the y component of the velocity vector, which was 30, over the x component of the velocity vector, which was 400 plus 30 root 3. And I don't think that's a nice, easy unit circle value. So you can just use a calculator to evaluate what that comes out to be. Might be nice to have it in degrees since everything else we've been doing is in degrees. So what does that come out to be? Yeah, Nick, so yeah, that should be right, Molly. Yeah, Darius. So Nick, to find the direction is always the inverse tangent of the y component of your velocity vector over the x component of your velocity vector. Does that make sense, Nick? Sure. So confident there. Yeah, I mean, the direction should always be inverse tangent of y over x, and it's always from the velocity vector. So. Because whatever the y value of your velocity is telling you how quickly you're moving in one direction, in the y direction, and the x value should be how fast you're moving in the x direction. So if you inverse tangent to two of those, the quotient of those, that should give you the actual angle at which you're moving. Any issues with that? Well, it's north of east because the angle you got out was 3.798 degrees. 3.798 is in the first quadrant, and it's just slightly north of going east. Suppose when you'd done this, you'd gotten like, negative 3.798, then you would have said it's 3.798 degrees south of east, or you could have said that it's traveling at an angle of 360 minus 3.798. No, Darius, you don't have to state the position vector. Molly, does that make sense or no? Okay. All right, everybody good? All right, let's do another one. Nice, easy one here. So we got a particle moving in a plane. We're given its position. These should be pretty straightforward to find the position vector. If we're given a coordinate that represents the position at any time, then that should just be our position vector. So this position vector should be sine t and t squared over 2. What about the velocity vector? How do we find the velocity vector? Just take the derivative, right? So our velocity vector should be cosine t, and this is 1/2 t squared, so the derivative of that should just be t. And what about our acceleration vector? Do it again, right? So derivative of cosine t should be negative sine t and 1. And if we want to describe the position and the motion of the particle at t equals 6, well, what's the position of the particle at t equals 6? It should just be the sine of 6, comma what? 18. And what about the motion? What direction is the particle moving at t equals 6? How do we figure that out? Should be the inverse tangent of what? Inverse tangent of the y component of the velocity vector, which is t, which is 6, over the cosine of 6. And what does that come out to be? It can be in degrees or it can be in radians. It doesn't really matter. Degrees are probably, I don't know, easier, I guess, just for the sake of being able to visualize what, 8.7 degrees is rather than trying to visualize what, 0.23 radians is. So 1.412 in radians, okay. And so what is that in degrees? $80.589. Everybody good with that? So let's take a look at the graph of this just for fun. If the angle is 80.589 degrees, no, that's fine, because we know what, Nick, we know what that means in terms of the angle. I just stated in the last one because it was kind of a real world thing with where we talked about the plane going directly east, so we said north of east. So let's see, we got sine t and t squared over 2, right? So here's the graph of this sine t and t squared over 2 from 0 to 6. So we can see that this is the path that the particle takes. This is its position at any given time. And then it certainly looks like it's at this value, whatever it was, sine of 6 and 18 at t equals 6. And yeah, it sure looks like the direction that it's moving in is about 80 degrees counterclockwise from the positive x-axis. Would you guys agree with that? So here's the particle starting at the origin and moving up. Everybody good? Okay. So this is all of the stuff that we've sort of been talking about, that a position vector, its derivative is velocity vector, the speed is the magnitude of v, our acceleration is the derivative of the velocity, and our direction of motion, like we said before, is this v over absolute value of v, which we said is the inverse tangent of y over x. Of the velocity vector. Everybody good with that? All right, let's see if we can do this one. All right, you guys good? You guys read it? Ready to get started with it? Okay, so we got a baseball player that's hitting a ball, hitting the ball at 60 degrees above the horizontal, and it's going at 110 feet per second. So what should the position vector of the ball be at any time t? Any thoughts on that? What is the velocity that the ball is traveling at? Should be 110 t, right? So our velocity is 110, so it's traveling 110 t, but it has to be multiplied by something because this ball is not moving at, directly horizontally or directly vertically. So if it's the x component that we're looking for, it should be 110 t times what? How do we get the x component? Yeah, times cosine 60, exactly. And what should the y component be? It should be 110 t times the sine of 60 degrees. But we need to do something else to that position in the y direction. What do we need to do with that? Anybody have an idea? Not plus 8. We're going to deal with that 8 later. That's a good thought because, right, the player is catching the ball 8 feet in the air, but there's something else acting on this baseball, not just the fact that it was hit at 110 feet per second at an angle of 60 degrees, but what else is acting on it in the y direction? Gravity's acting on it in the y direction. And so what do we need to subtract from this? What's pushing it down at, if we're talking in feet per second, what is the position, if we're using feet per second, that, or how is the position affected by gravity at when we're doing it in feet per second? What is the speed of, or the acceleration due to gravity in feet per second? $29.4. No, not 29.4, Elon. It's about 32 feet per second. And so if the acceleration due to gravity is 32 feet per second squared, then the velocity of the thing should be the integral of that, which would be 32 t feet per second, and then the position should be affected by how much? The integral of that, which would be minus 16 t squared. So something you'll want to keep in mind, that if you've got something that's affected by the acceleration of gravity and you're dealing in feet per second, the position of it should always be, the y coordinate of the position of it should always have a minus 16 t squared subtracted from it. If gravity is, acting on that object. Good or no? So if we start at negative 32 feet per second squared, Delphine, and this is an acceleration due to gravity, right? So if you integrate that, then you got negative 32 feet per second, and then the position, negative 32 t feet per second, and then if you integrate the velocity to get the position, it should become negative 16 t squared. Feet is how much it's affected. Does that make sense? So if the acceleration is negative 32, the velocity is negative 32 t, and then, position is negative 16 t squared. Good or no? Okay, so can we simplify that down by simplifying out the cosine 60 and the sine 60? What does that become? Cosine of 60 is what? Half, so that should be 55 t, and then the y component should be, if sine of 60 is root 3 over 2, that should be 110 root 3 over 2, or 55 root 3 times t. And then minus our 16 t squared. Good or no? So there's our position vector. So what's our velocity vector? What's the x component of our velocity vector? 55, good. And what about the y component? 55 root 3 minus that 32t that we got from the velocity. Good? Everybody good with the velocity vector? All right, so next thing we want to know is at what time t does the fielder catch the ball? So what is that telling us that we need to do? What's the only thing we know about when the fielder catches the ball already before we start trying to do anything? Right, it's when the y position is equal to 8, exactly. So all we need to do then is take our y component of our position vector and set it equal to 8, exactly. And it's from the position vector, so we'll say that's y equals 8, which is equal to 55 root 3 times t minus 16t squared. That's just a quadratic, so you can go about however you want to solve that. But you should be able to just use your calculator to solve that. So if you got your calculator in front of you, just graph y equals 8 and graph 55 root 3 times t minus 16t squared and figure out where those intersect. So somebody solve that and tell me what that comes out to be. Just give me a nice decimal on it. We don't need an exact value here.
What I like about summer is I can write as much as I want. Oh, damn, my pipe.
Anybody got a value for that? That doesn't sound right. I don't think 1.17809 is correct. I don't think 0.0852 is right either. I got 5.9. So I got 5.92 or something like that, close to what Darius got.
I was the one that said I get to do my bike all day.
All right, I must have just typed something in slightly wrong. So we'll call that 5.869. A couple of you got that. 5.869 seconds afterwards. And we want to know then how far is he from home plate at that time? So how far is he from home plate? How do we figure that out? That's the x coordinate of the position, right? And so now we have a time, 5.869, at which we're looking for the x coordinate of the position. So 55 times 5.869 should be what? Should be 300 something, I guess, right? 322.795. And what was this in feet, right? Everybody good with that? Any questions on that so far? All right, what about the last part here then? We now want to know how fast is the ball traveling when he catches the ball. So how fast the ball is traveling should be the what? Yeah, we're looking for speed here. And so what is the speed of that ball when it is caught? What is the speed of the ball at 5.869 seconds? So how do we figure out the speed? Should be the absolute value of our velocity vector, right? 55, right? Magnitude of the velocity. So 55, comma 55, root 3 minus 32 t, and t is 5.869. And so that should be the square root of 55 squared plus whatever this thing is squared. And what does that come out to be? $107.655 sounds good. I'm not sure about 63 or 55. 107 sounds pretty good. Anybody else get that 107? Yeah, a couple people with the 107. That sounds good to me. 107.655 feet per second. Those of you that got a different number, you guys try and plug that in again. Make sure you get the right number. Everybody good there? Any questions on that? Everybody good? All right, we'll do a couple more. This one's nice and easy. So we've got a particle that moves in the plane. We're given its position vector. We just want to find the velocity and acceleration vectors. That should be exceptionally easy. What should the velocity vector be? What should our velocity vector be? Three cosine 3t. And what about the y component? Negative 5 sine 5t. And what about our acceleration? What's the derivative of 3 cosine 3t? Should be negative 9 sine 3t. And negative 25 cosine 5t. Easy enough? Easy. All right, last one we're going to do today. So you guys want to try and do this one on your own and see what you can get. You don't need to bother with the part at the bottom where it says sketching the path of the particle and showing the vector and whether it's traveling clockwise or counterclockwise, we're not going to worry about any of that. In fact, we'll just get rid of that.
Come on, man.
So why don't you guys see if you can do all of this one on your own. I'll give you about, what, 4 or 5 minutes. That should be enough, yeah? You guys got this one finished up, or you need another minute or two? You guys good or no? You need another minute? All right, another minute or two. All right, what's your velocity vector? Should all at least have the velocity and acceleration vectors. So what's the velocity vector? Just 4 cosine t, negative 2 sine t. And your acceleration vector should be what? Negative 4 sine t and negative 2 cosine t. All right, and then to find, it just says find the velocity and the acceleration. The velocity should just be the vector that represents the velocity at pi over 4. So the velocity at pi over 4 should be 4 cosine pi over 4 and negative 2 sine pi over 4, which is what? 4 root 2 over 2, or just 2 root 2, and negative root 2. And then our acceleration at pi over 4 should be negative 4 times the sine of pi over 4, which should be negative 2 root 2 and negative 2 cosine, which would just give us negative root 2. Everybody good with the velocity and acceleration at pi over 4? Okay, and the speed should be the magnitude of the velocity vector at pi over 4, which should be the square root of 2 root 2 squared plus negative root 2 squared. And 2 root 2 squared is 8, and negative root 2 squared is 2, so that's a speed of root 10. And our direction should be what? Our direction should be the inverse tangent of our y-coordinate of our velocity vector, which was what? Negative root 2 over 2 root 2. And what is the inverse tangent of that come out to be? Negative 0.463 radians. People agree with that? Negative 0.464, 0.463. And so normally when we talk about vectors, we always talk about a positive angle. And so what's the positive angle of negative 0.46 radians? Or what we can also call it negative 20, what was it, 26.565 degrees? So we took the inverse tangent, gave us this negative angle in the fourth quadrant. So how would we write those as a positive angle? Would be, yeah, 333.435 degrees, do 360 minus it, or 2 pi minus the 0.463, which, I don't know, what does that come out to be? 5.820 sounds good to me. Any questions or issues with that? Until we get into doing integration stuff, you shouldn't have a whole lot else that you need to be able to do with vectors other than this. So hopefully that's pretty straightforward. Yeah, so Darius, you always want to have the positive value. I think way back at the beginning when we talked about the direction of a vector, somewhere in here, it's the smallest non-negative angle. So we talk about the direction of a vector, we always want it to be positive. Any other questions on that?